In 9.4, we're going to talk about trees, and as the book mentions, the definitions that we'll be using here are both familial and botanical. So we have animal and vegetable-based definitions here. Terms that come from family trees and terms that come from trees as plants, and sometimes upside-down trees as plants. But a tree is a connected, undirected graph with no cycles. It's acyclic. Alternatively, we can say that an undirected graph is a tree if and only if there is a unique, simple path between any two of its vertices. So we're not repeating any vertices along the way there. Looking at this example, the leftmost graph is a tree. I can get from A to B to F, for instance. There's a unique path going there. If I want to travel between B and L, I can go from B to A to D to G to L. That's the only way of doing that. However, if we're looking at this center one, this is not a tree. If I want to go from B to L, there are now two ways of doing that. I can go to A and then to C, then to L, or go from B to A to D to G to L is another way of getting there. We also have the cycle down here. So we have a 3 cycle here, and we have a 5 cycle along these edges from A back to itself, whichever starting vertex you want to use there. The rightmost example is not a tree because it's not connected. I have no way of getting from A to D. However, each of the components of this graph, each of the pieces, are themselves trees. And so we would call this a forest. It's a graph without cycles, but isn't necessarily connected. And so this is a forest. We have a tree, a forest, and nothing. So the next theorem gives us a relation between certain types of graphs and the number of edges. A connected simple graph with n vertices is going to have at least n minus 1 edges to it. In order to be connected, we have to have at least those n minus 1 edges so that we can go from one edge to the next and have it connected. We could have more if there are additional connections between vertices, such as what we have here. An acyclic simple graph with n vertices is going to have at most n minus 1 edges. So if we add another edge to that, then we're going to create a cycle somehow. And in part 2, this isn't necessarily connected, so we don't have to make those connections, something like what we have over here. And then a tree satisfying both of those conditions. It's a connected simple graph, and it's also acyclic. And so it's going to have at least n minus 1 and no more than n minus 1, which means that it needs to have exactly n minus 1 edges. So a tree on n vertices, we know then exactly how many edges it's going to have. A directed or rooted tree is a tree in which one vertex has been designated as the root, and every edge is directed away from that root. And then there's going to be a unique path from the root to every other vertex. Now the convention with a rooted tree is to go ahead and rearrange the drawing so that the root is the highest one, which is a little opposite from how real botanical plant trees work. But we're going to put the root at the top and then assume that the edges all go down and away from the root. So the way that we've drawn example 24, if I'm designating A as the root, this is the way that we would draw it. And we're going to think of all of these edges having direction, again leading us away from the root. Now, it would be fine to define B as the root instead, or redefine B as the root. So we'd have these directed edges here. Don't necessarily need to put all of these on, but since we've gone that far. If we designate B as the root, then all of the edges need to be directed away from B. And that means that this edge between A and B would then change its direction. And again, the convention, if we were going to do that, would be to then redraw the graph so that B is the highest and everything else is flowing away from it. Now, sometimes it doesn't really matter if the tree is directed or not. But in this definition, if we have a directed or rooted tree, then if we have a vertex other than the root, then the parent of that vertex V is the unique vertex such that there's a directed edge from U to V. So for instance, just pointing out some examples here, In this example, if I'm looking at I, again, thinking of this as a rooted, directed tree, everything is directed away from A since that's the highest one. And if we focus on I, then the edge would be pointing like that, so D would be the parent of I. And then reversing that, D, all of the vertices that have it as its parent are going to be the children. So G, H, and I are the children of D. Vertices that have the same parent are called siblings, so G, H, and I are siblings. Ancestors of a vertex other than the root are all the vertices in the path from the root to that particular vertex. So if I'm looking at F, then B and A are the ancestors of F. If I wanted to look at, say, vertex N, then K, E, B, and A would be N's ancestors. The descendants of a vertex, V, are the vertices that have V as an ancestor. So the descendants of B would consist of E, F, J, K, N, O, and P. So everything that comes after it. A vertex in a rooted tree is a leaf if it has no children. So for instance here, J, N, O, P, F, C, L, M, H, and I are all leaves in this tree. Vertices that have children are called internal vertices. So the root is an internal vertex unless it's the only vertex, in which case it's also a leaf and we just have a single vertex and no edges as our graph. So not very interesting. In this case, the internal vertices are going to consist of A, B, E, K, D, and G as our internal vertices. If we have a vertex in a tree, then a subtree with A as its root is the subgraph consisting of that vertex A and all of its descendants along with the edges incident to those descendants. So for instance, if I had the subtree rooted at B, then that would look like that. So I'm just going to cut off that edge from A to B and then focus on that tree itself. The level of a vertex is its distance from the root, and we'll think of the root as being at level 0. And then its children are at level 1, and so on. So here we could draw some dotted lines to indicate the various levels. So anything above that is level 0, just A by itself. And then B, C, and D are at level 1. E, F, G, H, and I are level 2. J, K, L, and M are level 3, and N, O, and P are at level 4. The height of a tree is the maximum of all the levels of its vert. So in this case, the height is 4. And a tree is said to be balanced if all of its leaves are at height h or h-1. So in this case, they would all need to be at height 4 or 3. That's not the case because we have these level 3 leaves or level 2 leaves at F, H, and I, and then C is a level 1 vertex. So it's not balanced. Our next definition is a K-ary tree. A rooted tree is called a K-ary tree if every internal vertex, anything that's not a leaf, has no more than K children. A K-ary tree is called complete if every internal vertex has exactly K children. And if we have K equal to 2, then that's called a binary tree. So we're going to look through and see what the largest number of children we have here is. That's going to be 3. A has 3 children, D has 3 children, K, vertex K has 3 children. So this is a 3-ary tree. But it's not complete because we have internal vertices. For instance, E only has 2 children. This is a complete 3-ary tree. All of the internal vertices have 3 children. Now we could still have a 3-ary tree if we were to delete, say, K, L, and M, get rid of all of the children of D, and just have D out there by itself. So we don't have to have all of them having the same number like this, or each of the descendants of one also having children. Or as another example, I could take E here and give it 3 descendants. So that's no longer a leaf. that's fine. I just can't take one of these leaves and give it just 1 or 2 descendants. That's not allowed. So if it's going to have any, it has to have 3. Now, knowing that we have a k-ary tree that's complete gives us some additional properties that we can work with. Now, the book doesn't state this theorem, but just so we can do another example, let's go ahead and talk through this. If we have a complete k-ary tree with n vertices, then it's going to have n minus 1 over k internal vertices and n times k minus 1 plus 1 all divided by k leaves. So we would know the k value. So that means as long as we know the number of vertices, then we can find how many internal vertices and how many leaves. So what the breakdown is between internal vertices versus leaves in that tree. If we know the number of internal vertices, then we can basically take these equations and solve for the other variables if we want to. We're going to have n equals k times I plus 1 vertices total, and then the number of leaves is going to be equal to I times k minus 1 plus 1. And then if we know the number of leaves, then we can find the number of vertices. We'll take k times l minus 1 and then divide that by k minus 1. And then the number of internal vertices is going to be L minus 1 divided by K minus 1. So again, knowing that the tree is complete and the K value, then we can find those. If we don't know that it's complete or k-ary, then these aren't going to apply. Let's look at an example. Suppose someone starts a chain email. Each person who receives it is asked to forward it to 4 other people. Some people do that, but some people don't send any of the emails. We're assuming that if they pass it on, that they're going to follow the instructions and send it to exactly 4, not more or less, but not everyone passes it on. So how many people have seen the email, including that first person who sent it, because presumably they saw it when they wrote it? If no one receives the email more than once, and if that email chain stops after there have been 100 people who read it but didn't send it out, and we want to know then how many people total and how many people sent the email. So let's break out some of our tree terms from this statement. Someone starts a chain email. Well, that someone is going to be the root of our tree. Each person who receives it is asked to forward it to 4 other people. So that will be our k value. Some people do that. Some people don't send any emails. And again, we're assuming that the people who do it are going to send it to exactly 4. So we know that the tree is full, at least under that assumption. So then how many people have seen this email? We're looking for the number of vertices, including the first person. If no one receives the email more than once, well, that's telling us that we actually have a tree. There are no cycles. And then we're saying that the chain ends after there are 100 people who read it but did not send it out. So the number of leaves is equal to 100. So that'll be our L value. So the total number of people who have seen it, that's going to be our N value. So using the formula above, we're going to have 4 times 100, our K value, times the number of leaves, minus 1, and then dividing that by 4 minus 1. That's going to give us 133 people who have seen the email. And then if we want the number of internal vertices, those will be the number of people who sent it on to someone else. So I is going to be equal to 133 minus 100. In this case, we don't have to go through the calculation again since we already have our n value. The number of internal vertices is just the total number of vertices minus the number of leaves, because everything else is an internal vertex. So 33 people sent the email on to someone else. Theorem 16 tells us that there are at most k to the h leaves in a k-ary tree of height h. We can look up at this example, and if I take away those edges. So this is a height 0, 1, 2. So height 2, we're going to have at most 3 squared leaves on that, and we see that that is the case. Here we have exactly 3 squared leaves. which is 9. Looking at this example, we have another 3-ary tree. The height here is 1, 2, 3, 4. So we're going to have at most 3 to the 4th leaves. And we don't have anywhere close to 81 leaves here. We have a total of 10 leaves in this graph. But that gives us an upper bound on the number of leaves in a k-ary tree of a particular height. And then if a k-ary tree of height h has L leaves, then the height is going to be greater than or equal to the ceiling of log base k of L. If the k-ary tree is complete and what's called balanced, then we're going to get equality. Balanced means that all of the leaves are at height h or h minus 1. Now the book just states it with the inequality, but that describes the condition that would be satisfied to have it equal to that ceiling. So if we go back and look at our previous example, we said we had 10 leaves here, and we can take log base 3 of 10, and that should tell us that the height is greater than or equal to that. We already know that we have height 4 here. Let's go ahead and compute that. So log base 3 of 10. Quick pre-calc review: if you can't compute that directly in whatever you have handy, you can use a change of base formula. It's natural log of whatever you're trying to take the log of. Divide that by natural log of the base, and you can use base 10 on those too if that's what you've got available to you. But either way, that's going to be equal to about 2.09. So that tells us that h is greater than or equal to 3. Taking the ceiling of 2.09 gives us 3. And that is what we saw in that particular tree. If we look at our other example here, since we have a 3-ary tree, we're going to take log base 3 of 9. And we don't need a calculator for that since 9 is 3 squared. That's just going to give us 2. And the ceiling of 2 is still 2. And that is our height that we have here. So that checks out in that example as well. Let's look at a couple of applications to finish off this section. The book doesn't get into binary search trees or decision trees. You may have seen binary search trees or will see them at some point in your comp sci classes, but we can create a binary search tree for this list of names. And what we're going to do is start with the first one. We'll have a way of basically ordering these alphabetically, if that's what we would like to do once we get done with this. We're going to start with Charlotte and make that the root of the tree. And then we're going to move on to the next name, looking at Rosie. That comes after Charlotte in the alphabet, so I'm going to branch off to the right then and put Rosie there. And then Arturo, well, that comes before Charlotte in the alphabet, so I'm going to branch off to the left. That, and then move on to Carla. Comes after Charlotte, so we come down here to the Rosie leaf at this point, and then we compare that to Rosie. Well, Carla's going to come before Rosie, so I'm going to put that to the left of Rosie. Check that off. And then we're going to look at Constance. Well, Constance, comparing that to Charlotte, is going to come after Charlotte. It's going to come before Rosie, so we go off to the left. And then comparing that to Carla, it comes before Carla, so it gets put down here. Then going through this, looking at Kenneth, comes after Charlotte, so when they move down to the right, compare to Rosie, comes before Rosie. Look over here, compare it to Carla. Kenneth comes after Carla, so we branch off to the right, like so. And then looking at Tracy, Tracy comes after Charlotte, so branch off to the right, and it comes after Rosie, so we're going to go to the right of Rosie. Then look at Jesse, comes after Charlotte, move down to the right, comes before Rosie, so we move down there. And then it's going to come before Carla, so move down, compare to Constance. Jesse is going to come after Constance, so we branch off to the right. And then look at Fred. Fred comes after Charlotte, before Rosie, before Carla, after Constance, and then before Jesse, so come down to the left here. Michael comes after Charlotte, before Rosie, after Carla, and then after Kenneth. So then we branch off to the right of Kenneth. And Michael is spelling his name E-L, or she, Mikhail. Now we didn't really do anything with this left branch here. Let's put something over there, say Bob. I'm going to go from Charlotte. Bob comes before Charlotte, so go over here to Arturo and compare that. Bob comes after, so branch off to the right and put it there. Now if we were to take this tree and start to sort of fold it up and collapse it, if I take Fred and put it up to, since we branched off to the left, I've put that to the left of Jesse, and then take all of that and fold up and put it to the right of Constance. So we'd have Constance, Fred, Jesse. Those would be in alphabetical order, and continue to sort of fold up the tree and collapse it in that way. So if we have whatever subtree came to the left of Charlotte, all of that's going to be listed before Charlotte. So we'd have Arturo, Bob, and then Charlotte, and those are in alphabetical order. And if we collapse up the right-hand side in a similar way, then we'll have all of the names listed in alphabetical order. Now there's another way of describing that in terms of the tree traversal. We're not going to be going into that here, though, but that's one way to think of that particular type of tree traversal. And then we're going to look at a decision tree on ordering the elements A, B, and C. So think of having three numbers and we want to put them in either increasing or decreasing order. We're going to start by comparing A and B. I'll just do A colon B. And looking at those, we could start with any two of them. We'll just say A and B. There are two possibilities. Either A is greater than B. We're just going to have some convention for how we decide to branch off here. So we'll say that if the left-hand side is bigger, then we'll branch to the left. If the right-hand element is bigger, then we'll branch to the right. So then branching here, this would be the A less than B. The B is the larger one. And then I'm going to take A, say, and compare it to C. If A is larger, then branch off to the left. If C is larger, then we go to the right. And in the case that C is larger than A, we already knew that A was larger than B in this branch, so now we know exactly how they are ordered. C is greater than A, which in turn is greater than B. So I'm going to put a circle there since we know the complete ordering. If A is greater than C, well, we still don't know overall what the ordering looks like. We know that A is going to come first, but now we need to compare B and C with each other. If B is larger, then we know that A, since it's greater than B, is going to be the largest, followed by B, and then C. We've got our complete ordering there. Or, in the case that C was larger, we know that A is greater than C, so A is still the largest, followed by C, and then B is the smallest in that branch. And that finishes our decisions there. Moving off to the other side, I'm going to extend this to give us a little bit more room. We compared A and B, so let's look at, say, B and C on this branch. If B is larger, B greater than C is going to then lead us to, well, we know that B is greater than both A and C, so we need to compare A and C, see where we're at. If A is greater than C, then we have enough information to completely order them. A is greater than C, and we know that B is greater than A here. So we're going to have B as the largest, then A, then C. On this side, C was the larger of the two, and here we know that A less than C, and then B is greater than C in this instance. And so B is going to be, again, the largest of all of them, but we'll have B, C, A. Writing it out in decreasing order there. And then finishing off this last branch over here, the only one that we haven't done, that would be C greater than B, or B less than C, and that gives us enough information. So B is greater than A, and then C in turn is greater than B. So C, B, and then A going from largest to smallest there. And that would complete the decision tree that we could go through to determine what the proper ordering is on those elements, again thinking of them as numerical values.